So welcome back to this chapter 2. But before we go into the before we go into the chapter, I just want to recap the differences between virus and a worm. Trying to get the start menu and get a table. Then maybe I can blow this up a bit. I want to get the whole screen interface, which interestingly is giving me a very small screen. Maybe let me just get rid of this side panel. Yeah, so so let me just recap with the differences between a worm and a virus. Basically, worm, virus. So the first real difference is really in the definition. We say that a worm is a fully fledged program. And this is a parasitic, it's really parasitic code which runs within a host program, Then, so that means that the worm is going to be larger in size, necessarily larger in size. And then this is going to be, smaller. It's going to have a smaller signature as a result. So of course we're saying typically. There's technically no reason why you can't write a large, but if the larger it becomes, the more easily it's going to be discovered. So typically, if it's going to be useful for anything in terms of causing havoc for the creator, they're probably going to want to make it a bit small so that it can be innocuous. So these are some of the differences. So this is fully fledged. The other thing is parasitic in nature. This is larger in size. The other thing is smaller in size, typically. Then this could be portable. It's capable of attacking multiple platforms. And this is very specific to the target platform. Well, I cannot think of any more differences at the moment. So just a small recap from the previous chapter. I want us to continue to the new chapter, which is a so-called technology trap. This is how we term it in the slides. So this is really just about. It's really about technology-related vulnerabilities. It's really just about technology-related vulnerabilities, and these include. We shall explain all these in a bit. Things like many IT managers, for instance, are not entirely covers that. So many IT managers are not entirely conversant with the technology, and this includes things like this could stem from issues like, for instance, there are managers who are obsessed with new technology, but new technology usually comes with hides vulnerabilities, because usually you'd assume that if you're an IT manager, that you will be conversant with the with old technology. You're going to be conversant with old technology. You know how it works. Yeah. If you've been using a system for the last 2-3 years, you're less likely to commit errors like, for instance, accidentally deleting files, because you know how the system works inside out. But there are organizations where you have an IT manager who is obsessed. They want to always update to the new version. Updating to the new version sometimes is not a good idea. So many organizations actually create, they're going to create a test system where they first test the new technology and see if it's going to, if it's bug free before they implement it into their production environment. So there are issues like, for instance, so I've already mentioned that one of the things that you probably want to do if you're in a production environment is to maybe have a test system. So the other issue, of course, is beta versions. Yeah. So many of these organizations that create software release what you call beta versions, where basically the point is for the public to test out the new release before it is actually becomes, you know, before it becomes a proper release. When it becomes a proper release, they call it a stable version. So it is, as a rule of thumb, it is not a good idea to deploy the beta version on your production environment. So, because this is essentially just being tested out, because in development they can test the implementation, they can test their new version on their servers, but then it is usually difficult to fully test the software, to understand the full range of things that can happen. So they usually release a version to the public to work out. And in many cases, for instance, if you're using Word, you can still, which is the stable version, if you're using like any version of a software, particularly in Windows machines, even after it becomes a stable version, there are errors because you cannot fully anticipate all the errors that could happen. And sometimes you see your software saying things like you encountered an error and asking you if you'd like to send the error back to the publisher. So it does happen, but those occurrences are usually more common in the beta versions. So if you have this kind of software that you don't really understand properly, it's a good thing to use a test system. But if you implement it to the production environment, then you are running a risk of an unforeseen vulnerability, of introducing an unforeseen vulnerability into the system. Of course, the other thing is the opposite. If you're obsessed, so failure to upgrade old systems. So if you fail to upgrade old systems, yeah, then of course usually many of the improvements that you have in new versions is more security. So newer versions usually have fixes. They usually have fixes for security issues. So particularly the stable versions, because when they release the beta versions, usually one of the things that they want to think about, they want to evaluate, is the security of the system. So in the beta versions, when the public use the community, usually refer to it as the community, when the community uses the systems, some of the things that they report are security related issues, and they will inform the publisher to actually make security fixes for the stable version. So in general, newer versions have got better security functionality. So you talk about security function, not necessarily security, because security is a result of the functionality, the capability of the system, and how well you use that capability. But in general, newer versions will have better security functionality than the older versions. Yeah, whether or not you actually use them correctly is really up to you. But in general, that's what's going to happen. So if you hold on to old systems too long, you could also, you could also be exposing yourself to security vulnerabilities, because the community will discover these vulnerabilities, and usually hackers are going to be part of this community, the user community. Then there are other things which are inherent in the way the technology works. In particular, we open standards. Here we talk about, we're going to really be diving into OSI, which is Open Systems Interconnection, I think. Open Systems So if you look at the modern computing environment, which is necessarily heterogeneous, yeah. So the modern computing environment is necessarily, just a minute. So I'm saying the modern computing environment is necessarily heterogeneous, yeah. So this heterogeneity basically means that heterogeneity comes at a cost, because it means that the different manufacturers are going to have to agree on certain things that their systems uniformly implement. Yeah, so they're different, whether you have an Apple or you have your Samsung smartphone or you have a Windows PC. They should be able to communicate within the internet. Yeah, so that means the only way you can communicate is that these different manufacturers have to agree on certain common functionality for their systems, and how they do that is via these open standards like OSI. So all the systems have got to implement OSI in an identical manner. So that means even before your attacker knows anything about your system, they know for sure that your system works a certain way, because that's the only way that your system can be able to operate on the internet. And of course, this creates all sorts of vulnerabilities because of the need to actually be able to communicate and understand each other. And one of the open standards that you're going to really look at is the OSI. So in short, in general, this is what the technology trap is really all about. It's really about technology-related vulnerabilities, which include session with new technology or failure, then secondly, the failure to upgrade old systems in time, and again, the other vulnerability, which is open standards. So let's just have a more detailed look at the OSI model. Usually I make the assumption that you already covered this in networking, but it's very important here, so maybe let's go through it again. So the OSI model is basically a model of how the network behaves. It is a model of how the network behaves, and just a minute. So it is a model of how the network behaves. So network functions are actually divided into 7 layers. You have the physical layer. I should probably start from application. You have the application layer. You have the presentation. So I'm starting from up going down. You have the presentation layer. You have the session layer. You have the transport. You have the transport layer. You have the network layer. You have the data link layer, and you have the physical layer. So when you have this So let me just copy this over and see. I need maybe to get one of these. Let me just snip it so that I can let me just snip it so that I can have it as an image. So now I have it as an image, so I can move it about. Let me just get another copy of that. And now I have two of them. Put this one on top. So if you have any two computers, they both have any two computing devices, they're both going to have an implementation of the OSI model for them to successfully communicate. And this could be, let's say this is a client machine. So this could be some client and this is a server machine, and both of them have to actually implement the OSI model. And how do they do this? Usually there's a procedure. So first of all is what you call encapsulation. So in this direction, you're having encapsulation. And then in this direction, you're having decapsulation. So we assume that these machines are going to be connected by a network. Let me just get a freeform. I don't know if there's a freeform tool. So you assume these are going to be connected by, they're going to be connected by a network. And this is okay, it's not really working out. Let me try to get a new tool. Well, I hope this is going to work. So you assume there's a network connecting this. So I'm assuming this is my network over here, connecting these two devices. So in order for these two devices to actually talk, they have to have a common language despite the different technologies that they're implementing. And so manufacturers have to agree that these machines will implement a common suite of functions. And these functions are layered into the OSI model. You could also have, on this network, you could also have an attacker over here. Maybe you have a man-in-the-middle attack of sorts. So the attacker also has to be able to basically, so this means that the attacker also implements the OSI model. But the vulnerability here is that the attacker knows for sure, as long as your machines are on the internet, then they are going to be able, they must speak this language. So the attacker knows for sure, even before they know anything about your system, they know that your system behaves like this, They know that your system behaves like this, so they already have a starting point. So this is a necessary evil that you have to actually bear with. So let us just, for purposes, we are going to do this once so that we understand what you're doing when you move forward. Let us just go through this actual process. How does it actually happen? So I'm going to begin from the physical layer. So let me assume that all these other processes have happened. All these other processes have happened. So we say that when you're going down, you have on the way down you have what you call the you have encapsulation. So on the way down, you call this procedure encapsulation. Then on the way up, you do the opposite. Yeah, on the way up, you do the opposite. We call it decapsulation. So in encapsulation, you add additional information. So basically what you're doing with encapsulation is, where's my cursor? So what you're doing with encapsulation. So at encapsulation, you are adding additional information. You add additional information to the message, additional control information to the message. Yeah, you're adding additional control information to the message to enable network passage, and communication with the recipient. Then at decapsulation, where you do the opposite, decapsulation, so it's not really an English word, it's a technical term. You are stripping away the control information from the received. So the receiver does this, they're going to decapsulate, they want to strip away the control information from the received message. So as to recover the original message. So usually like to use the envelope how do you call them, the envelope, so we like to use the envelope example. I'm looking for the actual term that you'd use in English, but it's sort of escaping. So in encapsulation, what you're basically doing is creating an envelope, and this envelope, what does it contain? It has got control information, and which is necessary to synchronize with the other host to agree on a bunch of things. So we get this control information, which has things like addresses and so on and so forth, which is essentially the envelope for the information. Because remember, the information, maybe you don't know this already, the information comes from the application layer, from the application, yes? But the application does not have a direct, it is not like a human being, it does not have a direct link with the application in the receiver, on the receiver end. So they have to go through the network. In order to successfully go through the network, they will have to agree, in order to successfully go through the network, then they will have to communicate via some communication channel. And to do so requires that that the sender and the receiver do implement certain things uniformly, that they speak a common language. Then at decapsulation, the receiver is going to remove that envelope, yes, to retrieve the message. So that is in short. In simple terms, that's what is really happening. So what's really going on at these different layers? What's really happening at these different layers? So maybe let me just get rid of this now. So I'm going to assume I'm going to use decapsulation. So I'm going to assume that we are receiving the message and we are going up. Yeah. If I take that direction, it's really the same thing in both directions. Then I'm going to start with the physical layer. So the physical layer is basically, remember the attacker also implements this, yeah, because his device has got to be OSI compliant. So the physical layer, first of all, is going to provide several facilities. And the physical layer, this is where you look at the physical media. For instance, are you going to use cable? Or are you going to use wireless? Yeah, cable versus wireless. The cable could be optical cable or it could be copper cable. This way, you're going to look at things like the maximum transmission distances. Yeah, this is where they're going to be defined. So maximum transmission distances. So of course, if I'm going to attack a system and I want to, for instance, to be successful, I have to be aware of how the actual physical medium works. One of the things is one of the strategies that is commonly used is to install a phantom device on your network. And in order to do that, then I have to understand the physical properties of the medium that you are using. So there will be things like maximum transmission distances. There would be things like transmission modes. So transmission modes are dealt with here. So transmission modes include things like, you know, are you going to be, is the communication half duplex? So this is very important for the attacker to understand and for the defender also to understand. Or simplex, or is it going to be full duplex? So this is important. This is important information for the attacker and important information for the defender. So you have to understand how does the then the other very important thing at this layer is clocking. Remember that at this level, the signal is actually just a bunch of voltage. They are really just voltage signals, yeah, voltage signals. So it is very important that the receiver, that the sender and receiver understand, synchronize their clocks, because they're really going to just count, yeah. They are going to count, and what they're doing is they're counting voltage signals, and these voltage signals, of course, the other thing here is the type of transmission, the type of signal. Is it going to be is it a digital signal, or is it going to be an analog signal? So these are things that have to be addressed at this layer, at the physical layer. Then of course, digital, the sorts of standards you have here include things like Ethernet. The kind of protocols that you have here include things like Ethernet, like FDDI, and all different. So you have this sorts of you know, standards that are defined at this level. So that's the physical layer. So the other, so the next layer then, once the data has been successfully obtained at the physical layer, is the data link. Is the data link layer. So the data link layer is going to have two sub layers. You have what you call the logical link layer, logical link control, logical link control, which is responsible for things like framing. So at the physical layer, the message is just one continuous stream. It's just one continuous stream of ones and zeros. I've said these are actually voltage signals, but at the logical link layer is when you begin to split it into the constituent. So it's one long sentence, but then you have to split it into the constituent words. And the words, we refer to these words at this level as frames, yeah, as frames. So you have to split the message. You want to split the message into constituent frames, yeah. So this is where you start the framing process. This is where on the way up, if you're doing encapsulation, yeah, if you're decapsulating, if you're going in this direction, if you are going down, this is where you actually, this is the last place the message should have already been split at the presentation layer. But now you're actually doing, when you're going back up, this, if you're going back up in the decapsulation side, then in the receiver side, this is where you actually begin to split the message into constituent frames. So that's framing, which is obviously very important. So the frame, we talk about PDUs. PDUs really just refer to we talk about PDUs or protocol, which are protocol data units. Yeah, so we talk about PDUs here, protocol data units. Yeah, so the PDU is basically the word. Yeah, it is the constituent word in the sentence. And the layer 2 PDU, the layer 2 PDU is the frame. The layer 2 PDU is the frame. Yes. So that is framing, and then the other thing, that's the logical link layer. Then apart from framing, you have so apart from framing, you have error detection and correction at this level. Yeah, you have error detection and correction, and you use things like so this is simple error detection to detect if there are any errors in the frame that has been set, and you use simple techniques like cyclic redundancy checking. So you have cyclic redundancy checking, then you have parity bit checking, and so on and so forth. Yeah, so you have simple techniques like this. Yeah, cyclic redundancy checking, parity bit checking. So you're checking for errors in the received frame. Yeah, so that's the logical link control sub layer. So the data link layer, so this is actually the lower layer, yeah, that we're starting with. Then you have the media access control layer, which basically you have the media access control layer. You have physical addressing, and then you have access, media access, yeah, physical addressing, which is part of media access. Then you have media access, which usually goes with a collision control. So the kind of protocols you have here, you have, for instance, collision sensor media access, carrier sensor media access. This is carrier sensor media access. With a collision so we have carrier sensor media access. You can have it with collision detection, as with on Ethernet networks, collision detection. So if you're on Ethernet networks, you're going to have this kind of setup. So this is for instance on Ethernet networks, yeah, Ethernet networks. Then you can have CA is collision avoidance. So that is carrier sensor media access with collision avoidance. Carrier sensor media access with collision avoidance. Then you could have token passing as another alternative technique. How did I get that? Okay, you can have token passing. So in Ethernet networks, for instance, if the device wishes to communicate with another device, yeah, let me just talk about this for a bit. So this is the media access layer, yeah. So let me just get rid of these protocols, because these protocols tend to make it look very confusing. So we said you need physical addressing, and then you need media access. Media access is basically to determine for the devices to work out how do they access the media, and why is that important? Yeah, why is that important? Let's just look at let me just create a new document here. Yeah, so why is that important? If you have devices on the network, you have that device. So at layer 2, we normally say that devices are on the same collision domain. At layer 2, devices are on the same collision domain. So let me explain what that means. It means so if you have, for instance, if you have a switch here, yeah, if you have a switch, yeah, so this is a switch, which is a layer 2 device, and you have your devices connected to the switch. Yeah, you have your devices connected to the switch. So these are different client machines. Yeah, I need one of those. I need to copy it. So you have your different machines which are over here. Here we go. So if we have this kind of setup, yeah, and then we you have device A, which is wishing to connect to device B, yes. So if device A sends a message on this network, actually this message is going to be seen by every machine on the network. So that's how it happens. If this device A sends a message to device B, it is actually going to be seen by the entire network. So we say they are on the same collision domain. So that means if what that really means is that if, for instance, device C happens to communicate the same message also to device E, then there will be collision on the network. Yeah, there's going to be collision on the network. So what media access is about is regulating, is about determining who gets to communicate. If you're using, for instance, if you're using a protocol like carrier sensor media access with collision detection, which is used with Ethernet, it means that first of all, the device, if A intends to communicate, it first listens to the network. It checks the voltage levels on the network, because it can know whether or not a device has communicated by checking the voltage levels, since they all see the message. So it will check to see the voltage levels if the network is idle by checking the voltage levels using its network interface card. So it will basically use its network interface, what we normally just call a network card. So it's a network interface card. Network interface card or NIC, yeah. So it's going to use this network interface card or the NIC, yeah. So it is going to listen to the network to see if there's any device that is communicating. If there's no device communicating on the network, then it is going to attempt to transmit. But sometimes it could be a case that C is also doing the same at almost the same time. So C has even already communicated, but there's a small time difference, meaning that the packets, rather the frames from C have not yet arrived at A. So A's network interface card is not able to tell that that communication has occurred. If it's not able to tell that communication has occurred, then it is going to communicate. It is going to transmit. But when it transmits, the two messages are going to collide. So that's what we call a collision. If the two messages collide, then A will notice this. A will notice by sensing that there's an increased voltage on the network, that there's a voltage which is out of bounds on the higher bound, beyond the higher bounds on the network. So A and C will know that there's a collision on the network. So that's what we call collision detection. So first of all, it will sense, because we say it's carrier sensor multiple access. Carrier sensor multiple access with collision. If you're doing collision detection, so it shall say it senses the voltage on the network, then it will detect that the collision occurred. So if a collision occurs, then they will create random clocks, and whenever these random clocks expire, then they will attempt to retransmit, yeah, and it will go on and on until eventually there's no transmission on the network and A can successfully transmit. But then I said that these devices at layer 2 actually in the same collision domain. They're in the same collision domain. So how does the recipient know that the message is intended for it? So it is because when A is sending a message, say to B, yeah, then it is going to add the layer 2 address, which is the media, which is the MAC address, the media access control address. And this address is physical and is contained in the network interface card. And how does A discover the media access control access for C? It will use an ARP request. So it is expected that there's an ARP server on the network. So ARP is address resolution protocol. So this is basically a table which contains so the ARP request is an request an ARP server, and the ARP server will have an ARP table. Yeah, it will have an ARP table. It will have. I need to insert just a table here to show you how this would look like in this case. So the ARP server is going to have an ARP table. You're going to have so the ARP table is basically a table which has got host IP addresses. Remember, because you could be asking where are we getting IP addresses from. So remember, this message is being originates from the application. It starts from the encapsulation side, yeah. So the message is actually coming from layer 3, yeah. The layer 2 message does not originate at layer 2. It actually comes from layer 3. So layer 3 will already have the IP, because the IP address is the layer 3 address, right? So the ARP table, which is going to be checked by the device to find out the MAC address of the recipient device, will have the IP addresses. We'll have IP addresses. I think you know what an IP address is. And then you'll have MAC addresses. So it's going to be a table that matches ARP addresses to match, rather IP addresses to MAC addresses. So it will have the IP for A. It will have the IP for B. It will have the IP for C. It will have the IP for E. IP for E. And then here you'll have the MAC. You'll have the MAC for A. You'll have the MAC for B. You'll have the MAC for C. You'll have the MAC for E. So if A wants to send to B, then it will have to first of all find out the MAC address. It will do an ARP request to the ARP server and then get the MAC address for B. And then it will add this MAC address to the frame that it intends to send to B, to every frame that is intended for B. And then it will send this. So for devices in the same collision domain, what's going to happen is that each device is going to see the message, like I said. So at media access, every device is going to see the message, yeah, because they are on the same collision domain. But then it will check the MAC address. So if a message is going to be, C will see the message, but then it will check the MAC address. If that MAC address does not correspond to its MAC address, then C is going to discard the message. C discards the message, and only B will process the message higher into higher levels. So what can an attacker do here? So types of attacks that you could see that are possible here are things like ARP, cache poisoning. So they can poison the ARP cache. So one sort of man in the middle attack is an ARP cache poisoning attack, where, you know, for instance, I'm the attacker here. Let's say I'm the attacker X, and I have somehow managed to install my device on the network. Yeah, I've somehow managed to install my device on the network. So if I can poison the ARP cache, it means, for instance, I can redirect messages to myself. Yeah, I can redirect messages to myself and make my device, or to any server that I wish, and make my device actually see and pick up those messages which are not intended for this device. So let's just go back to here. So this is what happens at layer 2. Then of course you have the IP, the network layer. So layer 2 PDU. So we said that layer 2 PDU is a frame. Then we have layer 3, which is the network layer. And the layer 3 PDU, or protocol data unit, is a packet. Yeah, the layer 3 PDU is a packet. So at layer 3 you have this is where you have logical, where you set up the logical network. Yeah, the logical connection. Yeah. Then you have routing. So the key thing you have here is okay, let me also put logical addressing. This is where you have the IP addresses, which are the logical addresses. Then you have routing. Routing is very important. So this is where you have, you know, so routing, you could use, for instance, IP addressing, or you could use circuits, virtual circuits, and so on and so forth. So you're going to have protocols. For instance, the obvious protocol you have here is Internet protocol. There's also things like IPX, which I'm not very familiar with, but I know it exists. So the key thing that you have here is routing, which I think you're very familiar with. Yeah, logical addressing. So basically, you have IP addresses. So this layer 3, the key thing you have at layer 3 is determining how to move your message from between networks, especially. Yeah, if you have in the same collision domain, of course, you do not have a very big issue. If you're in the same collision domain, you do not have a very big issue with there's no need. Routing is not a problem because all the devices are connected to the same switch. Yeah, here all your devices are connected to the same switch. But if you have so many networks of this sort, let me just edit and copy this, then do something like how do I select everything here? So if you have this kind of situation, now, so now we are going to have a different situation. I'm just trying to create a network here really quickly. So assuming this is a small network, then you're going to have a layer 3 device. So the layer 3 device, the common layer 3 device, is a router. So let's say we have our router here. So we have a router, yes. I should usually denoted by a circular, you know, kind of a diagram. So if let me just copy this again. So I need to have multiple examples of these. So now So we have our network here, yeah? So that's one network. Then we have a remote, then we have a remote network. So this is our remote network over here. So then we have, you know, so let's say we have these three networks over here, yeah. So typically these are going to be connected via let me just send this back. So these are going to be connected by router to router connections. So you're going to have this sort of thing, yeah? You have this sort of thing. So this is our network, yeah? So usually you're going to have to, so the router is going to have to determine, for instance, if this router wants to communicate, if this network wants to communicate with that network, so it is actually possible that within this network there also are additional routers. So it has to determine a route in order to reach this network. In this case, there's no determination to be made because there's only one route to the network. But it's possible, for instance, it's possible to have multiple routes. Let me just show you. Where did it go? Copy. So it is possible to have multiple routes to the target network. So I need to just send this to the back. So we have a situation where you actually have multiple routes at network. So it has to decide, does it go over here or does it go over here? Yeah. So what the layer that is responsible for this is the layer 3 is layer 3 or the network layer, and it does this by a process called routing, which I know you are familiar with. So it is very important to so the kind of attacks that can occur here again are very similar. For instance, you can have let's just look at the possible attacks. So what possible attacks do you think you can have here? So of course you can one of the possible attacks you can have is spoofing. I shall talk about this more later. So spoofing is one of the possible attacks that you can actually have here. So in spoofing, you actually can fake. Okay, what did I just do? So let's just so spoofing. So an attacker who is positioned on a network can actually spoof a host. So spoofing is assuming a false IP address, a false IP address. Yeah. So if I'm an attacker on the network, I can somehow impersonate this network over here by spoofing the IP address of the router, of the gateway router. So that means that information that is destined for this network here is actually going to end up on my device. And that can happen because the sender is going to trust that the receiver, by default, the sender trusts that the receiver is genuine, right? The sender will trust that the receiver is genuine. And other machines on the network by default will assume that the receiver is genuine, that the IP address that I have is actually genuine. So it is possible for me to actually spoof an IP address, the IP address of a receiver, if I know the IP address of that receiver. So anyway, let's go to layer 4. Let's just talk about layer 4 briefly. So layer 4 is the transport layer. So for the remaining layers, I'm going to just talk about them generally. Transport, session, presentation. I think I'm going to really stop at the transport layer. I'm going to stop this at this transport layer. Otherwise, it will become a networking. So the transport layer is where you have reliable transport. Reliable transport is where you have fragmentation and reassembly. Is where we have fragmentation and reassembly, reliable transport. So this is where you actually this is where you actually form the logical connection between the first machine, between the sender and the receiver. So reliable transport, maybe let me first talk about fragmentation and reassembly. Remember, the message originates from the application layer and then it goes to the presentation layer and so on and so forth. So at this PDU that we've been talking about here, it actually originates from layer 4. It is at the transport layer that the message is broken down into different components. It's where the message is broken down into different components, into different words. Yeah, it's where it's broken down into different words. Or so if you're going down, you're fragmenting. Yeah, if you're going up, you are reassembling. Yeah, so if you're going up, either you break down, or this is where you actually build back the message into its component parts. So there's another thing that I was going to forget: flow control. So at fragmentation, in order to reassemble the message, you have to give sequence numbers. Yeah, sequencing. Yeah, sequencing. Because remember, originally, let me use the binary notation. The message is something like this. So you have so many different messages of this sort, yeah, which are something like this, originating from the application. Yes. So when you fragment, you're going to have something like this. Yes, you're going to have something like this. Let me use a semicolon to demarcate different messages. So if I receive this first message, then how do I know that these packets actually belong to the same message? Yeah, so it means I have to have a sequence. I'm going to add a sequence number. Yeah, I'm going to add a sequence number. So let's say this sequence number 0 for the first message. This is sequence number, so these are packets from the same sequence number 0. Yeah, so these are packets from the same message, or segments. At layer 4 we call them segments. Yeah, so the layer 4 PDU is a segment. Layer 4 PDU is a segment. Yeah, so a segment of the message, right? So how do I know that these segments belong to the same message? Is because they have sequence. They have the sequence numbers which are following themselves. Yeah, so this could be sequence number 0, sequence number 1, sequence number 3, and so on and so forth. So then I'll have to, at reassembly, then I'll know which sequence numbers belong to which message. Yeah, so then I can reformulate the message. Yeah, if they have sequence numbers that follow themselves, then I can reformulate the message at layer 4, right? So sequencing is very important for reassembly. But then the other thing, of course, why sequencing is important is that then I can have reliable transport. I can have reliable transport. So both fragmentation and reassembly and reliable transport require sequencing. What do I mean by reliable transport? At layer 3, some of the protocols, particularly the most widely used protocol, which is IP, At IP, you do not have a guarantee, yeah? Because remember now the message is in packets, yeah? You do not have a guarantee that packets that belong to the same message or packets that are consecutive, that have consecutive sequence numbers are going to arrive at the router, at the receiver in the same order, yeah? You do not have any guarantee. So if, for instance, if you have, we say this is router A, which is the sender, yeah? If that is router A, which is the sender, let me just format this shape, remove the, then remove the line, then so we have, so if this is router A, which is the sender, yeah, then this is router, where did I put that? So if you have router A, then you have router B, yeah, which I'm failing to get. So okay, I was trying to label this. Okay, let's say this is router B over here. If you have router A as the sender and router B as the receiver, but router B won't work for me. Okay, let's say this is the sender and this is the receiver. Like we said, there's multiple routes that the packet can actually take to reach over here. So there's no guarantee that packets belonging, because this decision at routing is actually made on a packet by packet basis. So there's no guarantee that the packet that if the first packet takes this route, that the second packet is also going to take this route. It is possible that at the time of transmission of the second packet, which belongs to the same segment, that this packet is actually going to take another route to the recipient router, which is over here. So it is possible that the packet which I sent at the beginning actually arrives last, and the packet which I sent last arrives first. So it is in such a situation where you have a jumbled message, you're going to need sequence numbers to reorder the message at reassembly, yeah, to recover the message. But also important, without sequencing, which I said is going to be used by both fragmentation and reassembly, and reliable transport. So it is possible that some packets are actually going to be lost, yeah. So without sequencing, you cannot know the packets which have been lost. So if you have a sequence of packets which you've received, and you find that some packets are actually missing, some numbers are actually missing, then you can request for a retransmission, yeah? You can request for a retransmission. So basically, reliable transport requires sequencing, and it also requires retransmission. So you're going to request for retransmission for that particular packet, and then you can reassemble the packets once you have received all the sequence numbers in the communication. Then flow control is also important at this level, because it's like we said, it is possible that for instance, that the sender is a higher model than the receiver, yeah. So the sender could be capable of higher speeds than the receiver, or for instance, the sender is using completely different technology from a different vendor. So if the sender is too fast for the receiver, remember when the receiver receives the messages, typically the network interface card is going to have a memory which is called a buffer, yeah. Then as it is processing incoming messages, the messages which have not yet been processed will be kept in the buffer of the receiver. But if the sender is too fast, then they are going to overwhelm the buffer, yeah. And if the receiver does not have anywhere to keep the incoming messages, then they are going to be lost. The messages are going to be lost. So before transmission, the sender and the receiver have got to negotiate a transmission rate. They are going to negotiate a transmission rate. And if anything changes during transmission, then the receiver can also continue to tell the sender to either reduce or to increase the transmission rates. Sometimes this does not have to be done explicitly. Usually, if the sender notices that the receiver is requesting retransmission very frequently, because if the receiver requests retransmission frequently, it could be a result of the fact that the receiver is overwhelmed and is losing a lot of packets. Yeah, in that case, they will request for retransmission. So then this will have to lower the rate of transmission. So this is very important to be aware of. So one kind of attack that you can think of that originates from the relationship between the sender and the receiver. For instance, a denial of service attack. A denial of service attack could intentionally, you could have a sender who intentionally overwhelms the receiver. Yeah, so that is the basis of the denial of a type of denial of service attack. So many of the attacks that we're going to talk about are not going to exceed. They are going to not exceed layer 4. So remember, this is a recap. I have no interest. I have no interest in teaching networking, but I'm just doing a small recap for so that we can follow the material. But the actual point, was that the actual point that we were looking at was the technology, the so-called technology trap, which I said is really about technology-related vulnerabilities. Technology-related vulnerabilities on the system. And these technology-related vulnerabilities include basically an obsession with new technology, then failure to upgrade old systems, then open standards. So all the things that we've been talking about regarding OSI have been basically, it was a discussion about open standards, with OSI as an example.